This section applies double integrals for the calculation of surface areas. We may define the surface area of a surface to be the limit of Riemann sums. The Riemann sum is formulated as follows. Look at the figure. And now surface z equal f of xy is made here, and over D, the domain D. Now, to get the Riemann sum, we partition the domain in x direction and y direction, and that is a subregion. Then we can find the corresponding subsurface. Rather than this area of general shape, we may try to approximate the surface with the tangent plane. And this tangent plane, so that eventually it becomes, inside this region, becomes a parallelogram. Let's see A, then A, and here that is in x direction delta x, so that in x direction delta x and y direction 0, and now in z direction that is f sub x times delta x. So that is vector A. Now vector B is similarly given for this component. That is now there is delta y, so that in x direction 0, but y direction the length is delta y, and in z direction, height direction, it must be f sub y, delta y. So these are two vectors, and its cross product and length, that is the area of the parallelogram formed by these two vectors. So this general surface area locally will be approximated by the area of this tangent plane. So it's a parallelogram. Okay. Now let's try to get A cross B. By using a well-known formula, we can get that determinant of ijk, vector A and vector B. After getting the determinant, we reach at this vector. So its length can be here square root of squared plus that squared plus 1. And delta x, delta y can be written as delta A. So in the limit of this Riemann sum, we have the following formula. Just this is integral over D, and limit of that, limit of this one is here. We have that term. So as an official definition, the surface area of the surface with Z is f of xy, xy is in D, and assuming gradient of f is continuous, is defined along with this formula. This formula is a simple expansion of the arc length formula. In Calculus 2, you learned how to get arc length. Okay, let's try to get arc length here from A to B. Y equal fx. Okay, y equal fx is given in this way, and x is from A to B. Then to get this arc length, you first partition the interval, and then for each subinterval, we try to approximate the arc length by the length of the line segment. And we can get this length by using Pythagorean theorem. That is delta x, that's delta y. so that the local approximate arc length will be here. There is delta x squared plus delta y squared. It can be written in this way. Divided by delta x squared, and outside we multiply delta x. Then there's 1 plus delta y over delta x and squared. In its limit form, it becomes 1 plus derivative of f squared and dx, right? So you got such a formula in calculus 2. So that is simple expansion. We have one more term here, right? So you can easily memorize and use it. Okay, let's try to solve the problem. Okay, find the area of the part of the paraboloid z equal x squared plus y squared that lies under the plane z is 9. Okay, let's try to visualize the surface first. Okay, there's z direction, there's x direction. In fact, this is x direction, there's y direction, and that is z direction. And the reason we are using this x direction is that along this rotation and up, that is the positive orientation in three-dimensional coordinates. So rather than x and y, z, we are using always x, y, z because it is the positive orientation. Later on, in chapter 16, we see the difference between positive and negative orientation. Okay. Now, the paraboloid z is x squared plus y squared. So that is given like that. And we have to cut it with the plane z is 9, so that like that. So that point is 9. Okay. We have to find the surface area of this, like some soup ball, and the surface area of this soup ball. Okay. And this one, z is x squared plus y squared, and under the plane, then looks like it is defined. And here the projected bottom area. Once we consider this one, then the bottom area will be a disk of, okay, what is this one? It must be 3, because from here, z is x squared plus y squared, and z is 9. Then from these two, we have x squared plus y squared equal 9. So yes, disk of radius of 3. Okay, so that is the bottom. That is the. So we may consider the surface area is defined over d, and the function is now x squared plus y squared. From this observation, we got now almost all. Okay, we have to get square root of f sub x squared plus f sub y squared and plus 1. Okay, f sub x, 2x squared. That must be 4x squared. F sub y, 2y. So therefore y squared and plus 1. So here area of the surface must be integral over d, and that is a scaling factor. Let's try to write down 1 first. 1 plus 4x squared plus 4y squared and dA, right? Now to get the integral, because d is a polar region, we may use the polar coordinates. Angle is from 0 to 2 pi, and r is from 0 to 3. Okay, so that is from 0 to 2 pi, and r is from 0 to 3, and we have to express this one as a function of r theta. Okay, that's square root of 1 plus 4 r squared. And dA must be r d theta. Okay, that one is theta independent. So the theta integration is 2 pi. Now, for that one, its antiderivative must be, there's half power, so that 1 plus 4 r squared and 3 over 2, half plus 1, that is the major part of the antiderivative, and we'll evaluate this from 0 to 3, but we have to put here a constant to match the equal. Okay, to find this one, let's try to make derivative with respect to r. Then there are 3 over 2 and 1 plus 4 r squared and half power, and derivative of this inside is the same as 8r. Okay, that is the same as now 12 and 1 plus 4 r squared, half power, and r. Okay, derivative of this one and that one, by comparison, we can see that 12 is extra. To eliminate that one, we have to put 1 over 12. Okay, so we found the one antiderivative. Okay. Yeah, from this the constant part, we have pi over 6. And from this evaluation, once r is 3, then now this is 9 times 4, 36, plus 1, 37. So 37 power 3 over 2 minus, when r is 0, then it's 1, so that we have 1 here. Okay, that's the final answer. Okay, let's move on. Find the area of the part of a surface Z is xy that lies within the cylinder x squared plus y squared equal 1. So already, okay, from this one, D is this side, inside the cylinder, which means that x squared plus y squared is bounded by 1. That is the region, and over the region, now surface is made, and we can use the formula immediately. First component is square root of f sub x, squared plus f sub y squared, and plus 1. Okay, now this is f of xy, x derivative is y, so y squared, and y derivative is x, x squared, plus 1. Okay, so the area of the surface must be double integral over D, and this component, square root of 1 plus x squared plus y squared, and dA. Now this is again a polar region. Theta, the angle is from 0 to 2 pi, r is from 0 to 1. So that is from 0 to 2 pi, and from 0 to 1, that is the square root of 1 plus r squared, and dA must be r d theta. Again, theta integration, theta independent, so we can get 2 pi immediately. And for that one, here, the antiderivative must be, the main part must be 1 plus r squared and 3 over 2. Once you are trying to get derivative from this one, then 3 over 2 and 1 plus r squared and half power. And from this one, we have 2r will come out. After comparing with this one, we have extra 3. So we have to put 1/3 here, right? And then now evaluating from 0 to 1. Okay, from now on, it's a piece of cake. So you can finish the computation. Okay? Okay, that's it. It is the end of section. Thank you.